through mechanical constraint, at this 53 millimeter elongation causes a slight bending after a certain threshold. Uh, we can see that the pressure-strain relationship confirms the control deformation, providing a quantitative basis for precise actuation design. So this is the result for our pressure. So when we are trying for the left movement, the blue graph is for our below 1 and the orange one is for below 2. So we use positive pressure in below 1 and negative pressure, or basically vacuuming the below 2 for to get the left movement, and the front movement is basically giving positive pressure to both belows, and the right movement is basically the vice versa of the left movement. And the elongation is, as you can see, is pretty linear up to 50 kilopascal, and the root regions expand most during pressurization, confirming design expectations. And as I mentioned before, the horizontal test setup, because it minimizes gravity effects. So this is the trajectories of our project. So as you can see, we ensured multi-degree of freedom trajectories in both front, left, and right motions. The linear regression fits directional consistency, as you can see from the graph, and the real-time angle feedback enables stable motion tracking with minimal drift across repeated trials. So to conclude, this project demonstrated the viability of industrial limiting bellows as actuators instead of soft robotic arms instead of normal silicon ones, because the normal silicon actuators actually have some limitations of bending and other stuff, and this industrial limiting bellows mitigates that problem. We achieved multi-degree of freedom movement beyond simple flexion extension, including the varus valgus movement. We ensured predictable, stable, and regulated motion, overcoming uncontrolled bending issues in prior designs. And we developed a functional sensorized platform suitable for rehabilitation and assistive robotic research. Our future work will focus on optimizing the below geometry and connector linkage for greater motion range and durability, because we saw some deformities in the simulation part. If I go back, yeah. So we observed mechanical constraints slightly at highest pressures at certain thresholds. So if we can mitigate that, then it will get more motion range and durability. And we are trying to explore advanced control schemes for adaptive model-based learning-based platforms. We are trying to integrate additional sensing modalities for better state estimations and conduct real-world user trials for rehabilitation scenarios. And we will try to scale design for wearable or portable assistive application using this control system. Thank you. That was it from our side. Any questions?
Very nice timing. Just before lunch.
Yeah.
Please, any questions? Yes.
Thank you for the presentation about the pneumatic actuators and versus electric actuators. Why did you use the pneumatic ones, not the electric ones?
So basically, we're focusing on the because our work is primarily focused on the pneumatic actuators. So we are not actually like looking.
What about the accuracy? Because as I know, electric ones more accurate rather than pneumatic ones. Did you compare the accuracy?
Not really, but this is the field of our research actually. How accurate can it be? I mean, with better. Yeah. Right.
Okay. Second question. Thank you. What about the pressure sensor? What type of pressure sensor?
It's BMP-2.
What type of pressure? It's air pressure or
air pressure.
I don't know.
No.
What type of pressure?
It's air pressure.
Why do you need air pressure, atmosphere pressure sensor in your project?
So basically, to get the simulation data, and we have to match with the simulation data that how much pressure is going into the bellows. So we have to calculate those using the BLD modules.
But in your simulation, it answers everything. I think it's not air pressure, right? It's different type of pressure on
You
the
can put air pressure. I mean, the pressure inside the below. You can show it in the ANSYS. You need to cross section it the mark. So, I think you can understand.
Is it stress maybe? Stress was
Stress is it's on the inner shell of or inner wall of the below.
because BMP is for measuring air pressure.
We made a closed enclosure right, to measure the pressure.
So we basically 3D printed a closed enclosure and put the BMP inside of it, and then put pressure through a motor inside of the enclosure, so we can measure that pressure.
Okay, thank you.
Any other questions? No? Please join me one more time. Shakir, that's you. Oh, that's you. Oh, Tanmoy. I know Tanmoy. Very good job. Thank you. So we wrapped up with the morning session, so now
Yeah.
it's time for lunch,
for lunch.
right?
Yes, yes, we can go to lunch.
Thank you.
Just here.
See you in the afternoon.
So after, all right.